Today, billions of smartphones and servers stream data across the globe. But in late 1969, the entire internet consisted of exactly 4 computers. ARPANET, funded by the U.S. Defense Department, allowed researchers to access a handful of room-sized computers from across the country. Its decentralized structure was designed to provide communication lines that could survive a nuclear strike. The network used a language called TCP/IP and a concept known as packet switching. If one path was blocked, the data would instantly find an alternate route to reach its destination. While the system was resilient, it was difficult to use. To connect to another machine, you have to memorize its exact numerical IP address, a long string of digits that computers use to identify one another. The only directory for these numbers was a single text file named hosts.txt. It was managed by a small team at the Stanford Research Institute. Adding a new computer to the network required a phone call during business hours, so a human operator could update the master file by hand. A decentralized digital network cannot scale globally if it relies on a centralized, human-operated phone book. If the internet was to grow, the directory had to be automated. The solution arrived in 1983, when an engineer named Paul Makapatris developed the Domain Name System, or DNS. Instead of forcing people to memorize digits, DNS maps a familiar web address to its corresponding IP address. Shortly after, graduate students at UC Berkeley wrote a software package called Bind. This allowed the DNS directory to be shared across multiple servers simultaneously. The network now used an automated, decentralized map that computers could update and query on their own, without a central choke point. DNS made the network easier to navigate, but it didn't change the laws governing who could use it. Because ARPANET was a defense project, access remained restricted to military contractors and elite researchers, leaving the broader scientific community on the outside. By the early 80s, engineers had built a robust navigation system for a digital world, but most academics and scientists were still legally barred from entering it. The National Science Foundation intervened in 1981, funding a network called CSNet to link university computer science departments together. This led to the 1985 launch of NSFNet, which used a 56 kilobit per second backbone to connect 5 supercomputer centers across the country. The pivotal moment came when the NSF opened this network to all academic and research users, removing the strict military-only requirements of the previous era. Usage increased immediately. Traffic on the academic network began doubling every 7 months, quickly overwhelming the initial 56 kilobit lines. To handle the surge, the government partnered with private industry. A team including IBM, MCI, and the Merit Network rapidly upgraded the backbone to handle data at nearly 30 times the previous speed. NSFNet effectively merged thousands of isolated regional campus networks into a single high-speed architecture. It had successfully created a unified network of networks. By the early 1990s, this infrastructure was routing trillions of bytes of data every month. The physical scale of the network was becoming too vast for a single government agency to manage. Policymakers realized the network had become a vital piece of national infrastructure that was now commercially viable. In April 1995, the National Science Foundation decommissioned its dedicated backbone and transitioned routing responsibilities to commercial internet service providers. This transition removed the final restrictions against commercial traffic. Within a few years, startups like Amazon were building global businesses on the infrastructure the government had established. The modern internet wasn't a single discovery, but a 30-year relay race. Defense research laid the foundation, academic coders drew the map, and public science built the highways that eventually allowed the entire world to log on.